lot of different variables, some algebra stuff going on here. So if that's your thing, you're going to really like it. If it's not your thing, then you need to have examples to refer to. If not, you won't be able to do your homework. Okay, so there are two isotopes of chromium 52, which weighs exactly this. Chromium 51, which weighs exactly that. Look at those units, AMUs, right? Atomic mass units. And in our lab, some of us didn't include units, period. So make sure you're using AMUs or grams, but AMUs is probably more relevant. The relative abundance is that and that. What is the average atomic mass? Tell me how to start this. Go for it, Natalie.
You have to multiply the percentage
By the what? Not multiply the percentage by 100. Divide it by 100, right?
Oh.
So when you divide the percentage by 100, you're basically moving the decimal back twice, right? So you can just tell me move the decimal back, and I understand what you're saying. So 98.2 is 0.982%, and then the other one is what? Point what? So you're going back 1, 2, so 0.018. All right, so that we've done that. We've taken the percentage to decimal form. What's next? Go for it.
You have to multiply the number
by this percent, right? Okay. So we're taking the mass of each of these. So for the first one, the 52 is 98%. So 52.225 AMU. And then the other one is 50.996 AMU. Okay? So the second step, we're multiplying across here. Tell me what you guys get for the first one and then for the second one. Shout it out.
So I got 51.28495.
82848.
28495.
495. Okay, AMUs, and then the second one?
0.917928.
And it's okay that these two numbers here are not sig figs because it's not our final answer. So first step, take the decimal, multiply by the mass of that specific isotope, and then what are we going to do with these? Add them up, okay? So this right here added together is what? 52.878. AMUs. All right, so then let's talk about sig figs here. Whenever you're looking at this number across and you're multiplying across, you're looking at limited number of sig figs of 3. Those 3 sig figs transform this into 51 point what? 3. Okay, so that's 1 decimal. Same, this one only has 2 sig figs, so when you multiply across, this should be what at 2 sig figs? 0.92. Okay, so this has 1 decimal, this has 2 decimals. When you're adding, you're looking at decimals, so how many decimals should the final result have? Just 1, because this was 2 decimals, this was 1 decimal. 1 decimal is your weakest link, so this should be rounded to 52.2. Yep, AMUs. So there's our final answer there. Yeah.
So do you round for the sig fig after you multiply?
I didn't round, so I kept that in my head. So because I don't want to round this and then round this and then kind of round again. That makes me round 3 times. I just keep in the back of my mind how many sig figs this really should have, which it should really have 3. This really should only have 2, and then consider that as your final step of your calculation. So like we just said, this should have 3 sig figs. This should have 2 sig figs, and so this should only be recorded to 1 decimal really. This should be recorded to 2 decimals really, and so when you're adding, you're considering the lowest decimals, which is 1. So at the very end, all right, so there's our average atomic mass. You'll see that come up again on your unit review and on your test for sure. Okay, so just put a star by that so you know how to do that. Any questions from last night's kind of research and finalizing some of those thoughts that you guys had to divvy up between your partners? Hopefully we did a little bit last night. Okay, tonight, just make sure just so you know, you can finish your history project because that's what we're presenting on Monday in our scientist committees that we're going to be meeting with. And we're going to start with the electromagnetic spectrum, and you'll be able to do about a third of concept 5. Okay, so just the ones relevant to what we're talking about today. Okay, let's talk about that. Modern model. So what does modern mean? Today, current, right? Historical model means what? Old. So the Dalton's model, J.J. Thomson's model, Rutherford's model, they're all kind of outdated. The very beginning ones are for sure outdated. The Rutherford's model is pretty, I mean, the part about the nucleus is true, it's still in the middle, but now we have a more modern model that explains a lot more about the electron. So today is really honing in on the electron and where it is and what it can do. Because it can do a lot of stuff. It can move around, it can jump up energy levels, it can fall down energy levels, and we can't really detect that. We see the results of it, we see light. So that's actually a lot, it's really relevant stuff today. So this is on your paper. You need to know a couple background definitions before we can really put some meaning to what we're saying today. So the little wave I have here, you know, waves come in bigger and smaller sizes. The amplitude is this part in the middle. The amplitude is the distance from the middle of the wave to the crest. And that's right here, amplitude. I don't know how much I actually explained on here. Nothing. You throw it. Okay. And that's important, but it's not important to our calculations. It's just important to tell us there's a little bit of an intensity of color difference whenever the amplitude differs. So really short amplitude would be a dim kind of light, and a high amplitude would be a bright light. The second, and these are some terms that you defined in Reading Guide 5, so you will hopefully paraphrase because there's some repeated stuff here. But actually, the more you see it, the more you know it, so it's all good. Frequency is labeled as V, so it's like V with a little tail on the side, kind of like that. So you'll see me write it as V like that, probably more than just a normal V. And so that is like, if you're standing on the side of, you know, Cotsmill Road, you're going to look for the frequency of cars that pass. So there's going to be a certain number that pass your point every so often, over a specific amount of time. So if you stood there for an hour, you would see a specific number of cars pass. Same kind of story. The number of waves that pass a specific point, so if I was standing here, the waves that pass me would be the frequency. So more waves would be a high frequency or low frequency? More waves passing. High frequency. Really low number of waves passing would be a really low, slow frequency. So I always relate this to rate or speed of the wave. Now we measure this in two weird units. Usually it's per second. So per second is just 1 over second, or hertz. So because this is a guy who discovered this, everybody names something after themselves. So it's either 1 over second or hertz. 1 over second can also be written as second to the -1. All that's equivalent. Okay, and then the distance, and this is indicated on the little image, the wavelength is the distance between the two crests. So radio waves have really, really long wavelengths because their crests are so far apart. They're taller than I am, where radio waves are huge. And then gamma rays are really, 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 really fast, but they're really, really short because their crests are really close together. So that's going to be represented by the Greek symbol lambda, upside down y. Okay, so know that. And this equation is a definite that you need to know. You need to know that. You need to memorize it. It's not, you're going to use it so much you're going to accidentally memorize it. So don't try to make flashcards. I think you'll be fine. But the two of these come together. The two variables come together in this equation. C is the speed of light, is equal to wavelength times frequency. Tell me how the units work out here. What are the units for the speed of light? They're on the board. Light years, that's meters per second. Okay, meters per second. Okay, so I'm just going to put the units there. What are the units of wavelength? I don't think it's up there, but think about wavelength. Length. Meters, good. So the unit of wavelength is literally a length. It's meters. And then what is the unit for frequency again? What is the unit? That's the variable. Hertz or 1 over second, right? It's not meters per second, it's 1 over second or seconds to the -1. 1 over second is how I'm going to write it here. Do you see how these work out to equal the speed of light units? You have to be able to see that because you have to be able to cancel them if we need to. And we need to work on canceling units sometimes. So meters over seconds, meters over seconds, meters over seconds. It all works out in the end. Okay, so what we're going to do is we need to first recognize that all energy, and I'm going to say light energy, there are some other energies that we will deal with today. We're going to really focus on light though. All energy moves at this speed, at the speed of light. Okay, so that means that we can create this relationship where if I know the wavelength of it, I can figure out the frequency of it because there's this constant speed of light. That's a constant, so C is a constant, and we will never change it. It's always going to be 3.00 times 10 to the 8 meters per second. Can I move on? Let's do some practice with this. Okay. Oh, let me show, well, I'll show you this and I'll show you a little video. I have like 4 or 5 videos I'm going to show you guys today. So, speaking of energy, it comes in lots of varieties, right? We've seen the electromagnetic spectrum before. Yeah? Okay, you know there's tons of different forms of energy. The one that we probably, hopefully will never feel are gamma rays, or we all will become the Hulk, right? That'd be awesome. But those are really, really, really short. Notice the wavelength here, 10 to the negative 14. Tiny. The ones we hear on the daily are the radio waves. They're huge. 10 to the 4th meters. Like that's that's only like 2 meters, right? The wind, what's this called? Wingspan. About 2 meters. So they're huge. The ones we see that our photoreceptors in our eyes are just capable of kind of interpreting as just this little tiny section of visible light. So we can see this. The other ones that we can feel are infrared. It feels kind of warm. And the things that are felt in a different way are UV. We usually feel a burn from that. So warm versus burn. I prefer warm, but not burn. The UV radiations also can damage your DNA because it's so small it can get in your cells and break apart your DNA, mutate it, right? So that's why they say put some sunscreen on so that it blocks the UV radiation from penetrating your cells and getting in your DNA and messing stuff up, so no cancer occurs. Okay, back to chemistry. So we need to know the units here in this particular model is in meters, and then as we come down here, it's in nanometers. Most likely, you will see wavelengths as nanometers. So get comfortable with the metric system. Nano is going to be the one we see a lot. So using this knowledge, we already know, let's say we have violet light, and I tell you that its wavelength is 400 nanometers. My question, you know how I do the whole question thing, the question is, what's the frequency? What do I know? What do I know right now about this problem? It's my given. What is 400? Wavelength is 400 nanometers. And then what do we know about the relationship between those two? It's an equation. They are multiplied to equal what? Speed of light. So we know this. So this should probably be written at the top of your paper. Okay? So write your formula, write your given, write your question, and then let's solve. Let's figure out how we're solving. This is just algebra, but we need to do a couple, so I don't assume that we know everything. Can I type this one up on your paper? Okay. So C is equal to lambda times frequency. What do I need to do to this equation to isolate V? Yeah, Hayden. Divide by lambda. Divide by lambda. So this means the lambdas here cancel. So V is equal to C over lambda. Let's just plug it in. Yeah?
Yeah.
Let's double check our units though first. Okay, I wanted somebody to say yeah. Thanks. C is what again? Meters. 3.00 times 10 to the 8th meters per second. If I put meters up here and nanometers down here, can they cancel? No, they are not the same thing. We cannot cancel unless it's exactly the same unit from top and bottom. So before we move on, let's write down our King Henry died by drinking chocolate milk. Now let's figure out how to convert from nanometers to meters. So I'm going to write this in red up here at the top of my paper. King Henry died by drinking chocolate milk, ... what? Micro, then nano, then pico, and on this side, mega. Okay, so from base, which is meter, here, base, which is meter, I'm going to make that a 1. How many zeros away is nano? You have to count the dots. Remember, they're placeholders. 9. It's 10 with 1 with a 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 zeros different, so I don't want to write that many zeros. That is way too much writing. So I'm just going to say 10 to the 9th nanometers is equal to 1 meter. That's our conversion factor. 10 to the 9th nanometers is equal to 1 meter. So when I have my wavelength right here, what do I need to multiply it as a fraction to convert to meters? What goes on bottom? Okay. So I got 1 meter over what? 10 to the 9th nanometers. So all that stuff from unit 1 is coming back into play here. Nanometers cancels. That should give us 4.0 or 4. I'm just going to do 4 since I don't have any decimal there. Times 10 to the -7th meters. That's our wavelength. 4 times 10 to the -7th meters. It's a little scrunch on the side. Okay, now we can actually tackle the problem. Now it's in everything's in a good place in terms of units. What goes in the numerator of our little fraction that we've set up here, our rearranged algebra? So 3.00 times 10 to the 8 meters per second over what? 4 times 10 to the -7th what? Meters. This looks kind of crazy. We have some scientific notation. We've got fractions of units up here and just a single unit down here. What you really just need to kind of step back and recognize is that there's, in the numerator, there's a meter. And the denominator, there's a meter, right? So those two can cancel here and here. And what's left? What unit is left? Not just second. What's the slash mean? Per second. Per second is left over. Okay, it's not just seconds. So frequency needs to be recorded as per second, right? 1 over second. So you guys, I need you to try this in your calculator right now. It's making sure that you can put parentheses around your numerator divided by parentheses over your denominator. Because your calculator is not going to know what you're applying the whole times 10 to the 8th and times 10 to the -7th is, unless you give yourself a little practice around here. So put parentheses around your numerator divided by parentheses around your denominator. Some calculators work the same. If you turn it sideways, the calculator should expand. What do you guys get? Times 10 to the 14th. And that should make sense, because do you remember when you have exponents and you divide them, what do you do to the exponents? Subtract them. So 8 subtract a -7 means 8 plus 7, right? What's that? What's 8 plus 7? 15, okay? But you're doing 3 divided by 4, so that's like 0.75, right? So that 0.75 times 10 to the 15th means the decimal scooches back 1 to make it to the 14th. So you can kind of make sense of it too. It's logical. So this is blah, blah, blah per second, right? You can write it like this, or you can say 7.5 times 10 to the 14th hertz, HC, hertz. Or 7.5 times 10 to the 14th seconds to -1. These are all equivalent. So just get used to seeing it in 3 different ways. Okay, is that hard? I think it's just detail oriented. I think it's like you need to look at your units, you need to rearrange your variables, and then you need to solve with the good parentheses in your calculations, yeah.
It's under the 7.5.
Here, per second. That's just an S a second. Okay, so that's how we calculate some variable about the speed of light or related to wavelength or frequency. Let's talk a little bit more about what these are used for, okay? So we're going to combine this with a model too. So this is something you've already written a little bit about on your history notes. So if you want to add anything to it, that's fine. But this is the Bohr model. Who's Bohr on Monday? Woo! I'm looking forward to some boring talks. Okay, so we have, I'm not really looking forward to boring talks. I want to hear you talk about Bohr. All right, we have a model that looks like this for Bohr. Looks kind of crazy, but we have energy levels. They expand from the middle and outward for where electrons live. Okay, so electrons live on these energy levels, and if it lives on an energy level, it has that specific set amount of energy. That is called quantized. So a quanta or quantized energy level means that the electron is set at that energy. So a specific amount of energy. If the electron moves from level to level, it gains a new amount of energy, or it loses a new amount of energy. So we'll talk about that in a second. As this amount of energy is lost or gained, sometimes it will put out energy as it's lost, right? So if you lose energy, it's going away. Well, if it's in that special spectra, in the visible spectrum, we can see it. If it's in the infrared area, we can feel it. If it's in the UV area, our DNA is going to get damaged, okay? So it's going to be put out in some way or form. If it's put out as a light wavelength, then we see it as a spectra. So a spectra means going from like red, orange, yellow, green, blue, purple. It can show a lot of different colors, or it could just show like just blue and green. Okay, it's different for every single element. So the spectral lines are something we're going to work a lot on Monday, but just know that it can put out a specific wavelength of light. So you can see that in this image by energy level 4. If the electron drops from energy level 4 down to energy level 2, all that energy is lost. And it's lost as a really a lot of energy, which is a high energy wave, which is violet light. So this is high amount of energy is violet light. This one, dropping from energy level 3 to energy level 2, only loses a little bit of energy. So low energy happens to be red light in color. Does that make sense from our EMS, the way we had it written? Maybe I need to draw it again for you. Let's draw this together. Here's how I remember it. You're gonna laugh at me, okay? Gonna X your voice in my radio. Okay, so gamma, X-ray, UV, visible, infrared, microwave, radio. Gonna X your voice in my radio. I had to make that up for myself because I can't remember this for anything. But gamma rays are little bitty things. X-rays get a little bit bigger. UVs are bigger, visible is bigger, and then we have like crazy long radios. That's not exact, not to scale there. That's the best I can do for wavelengths. So these have, this is a good way to kind of remember which is the short end of the stick. Which one's the short end of the stick? Gamma. Okay, so this is short wavelength. These are long wavelengths. Who is high energy? Who makes you the Hulk? Gamma, yeah. Microwaves. Like the actual microwave that you heat your food up with, right? What's up?
It's invisible. What's the
IR, infrared. Okay, so short is high energy. So I was thinking of my little dog. She's really short, but she's a crazy dog. She's like so hyper. So she's a little, her name is Ellie. She's a little Alaskan Malamute Labrador mix. She's so cute. Husband does not like her, so I have to give her all the love. So she's short and high energy. And then I have Wally, who's the Great Dane, who I can ride like a pony. He is really like lazy, really low energy, and he's very long and very tall. He stretches across the couch, and he's actually taller than me when he stands up. So that's how I remember that too. You guys will have to come up with your own, or you can take on my dogs. That's cool. You can like them just as much. So that is the electromagnetic spectrum kind of in a nutshell. All right, can I go forward? Let's do some more practice with the Bohr model. So what I was saying, the Bohr model, when the electrons lose energy as light, we can see it if it falls in this spectra, if it falls in this specific section of energy. Okay, so these are the important parts, and we're going to do 2 labs on them next week. You can draw some images if you want to, but I'm just going to tell you about the terms we use, like excited and ground state. So if we have a particular atom and the electron lives in this particular energy level, that is its set amount of energy. Well, we can excite electrons with lots of types of energy. Specifically, you can excite them from their ground state. Remember, ground state's where they naturally live. You'd excite them by shining light on them, heating them up, electrocuting them. Pretty much any form of energy you throw at them, you can excite an electron with it. So when this electron gets excited from its ground state, it absorbs, in this case, we're shining light on it. We're exciting it with light. We can also excite it with those other things, electricity and so forth. It's going to absorb that energy, right? So this is stage 2. It's absorbing the energy. So 1, 2. So like if you were trying to tell somebody, DIY, how to excite an electron, here you go. Make it, allow it to be existing in its ground state, shine light on it, it will absorb that light. Remember, light and photons, light mean, or photon means light. And then you'll make it go to its excited state. And you'll see that this energy level of energy level 2, the electron jumped to energy level 3. I know it looks like it went down, but it actually just went up to this outside energy level, and now it's just circulating because electrons are always orbiting. So that's now excited. If you're on a caffeine high or a sugar high, how long does that last? Not long, right? It's not going to last long. You're going to crash back down to stable ground state. This electron will do the same. It will crash back down to its ground state. So as it goes back to ground, as it grounds, I'm going to say it like that, it's going to release that extra energy, and that's when we can see it. We can see it release energy as light. So as they fall back down, they emit light to release energy. So that's a very important phrase if you need to write that down as well. Sorry to save a lot of notes today. Images, Bohr model, calculations, so forth. And if that energy falls in the visible spectrum, then it will look like a specific wavelength. So the energy emitted can be equal to a photon with a specific wavelength of color. So red are short or long waves? Red are long, they're on the infrared side. Violet, short, is on the ultraviolet side. So we just drew that out. Okay, so Bohr's model again, what we were just talking about were energy being emitted, and as energy is emitted, we can see it in an emission spectrum. So this is from a specific element. Every element has a different emission spectrum because does every element have the same number of electrons? No, so every element has a different number of electrons, so there's different things they can jump up and down to and release light. So when that happens, it creates this little bright line spectrum, so that's another term for it, where you can see the individual wavelengths. Opposite of emission is absorption, so you can see it's just inverted. You see that? So you have black here but red here, red there but black there, and so forth. So this is an absorption spectrum. That's the different wavelengths of light they absorb. These are the different wavelengths of light they emit. So it's all about wavelengths of light. Okay, the continuous spectrum is one that only a white light source would be able to put out, like the sun. So the sun is a really good example because it has hydrogen and helium, but it also has a huge emission spectrum, so it's actually continuous. There's no gaps. Okay, you guys want to take a break and watch a video real fast? Okay, you've got those long faces. Try to make sure you're still with me here. So let's do let's do this one. Or this music. Okay.
The electromagnetic spectrum, an immense scale used to measure the wavelengths of all kinds of radiation. At one end are radio waves with the longest wavelengths. At the other end are gamma rays with the shortest. In between are the other bands, including visible light, which is such a tiny fraction of the whole, it's difficult to imagine. How small is the visible spectrum? If you had a reel of movie film representing the entire electromagnetic spectrum, stretching 2,500 miles from California to Alaska, the section containing the visible spectrum would fall somewhere in the middle, near the University of Washington.
This frame is the whole visible spectrum. It is one frame and over 2,000 miles of tape, and it's everything that the human eye can see. The importance of this frame is that stars emit almost all of their light in this part of the spectrum.
And even though the light is visible, it still contains hidden tools. The secrets are in the spectrum itself. The visible light in this lamp comes from hydrogen gas excited by electricity to form a glowing plasma, similar to what happens in a nebula. By viewing the lamp through a diffraction grating, we can split the light up into 3 narrow lines on the spectrum, a virtual fingerprint of light, unique to hydrogen alone.
So in the spectrum, you see 3 features. One is red, one is a light blue, and the other is a deep blue. This pattern of wavelengths is absolutely unique to hydrogen, and there's no way to confuse hydrogen in the spectrum with any other element.
So we're actually going to do that on Monday. Woo! So we're going to get to see the fingerprints of the atoms. I don't want to cancel. No, oh no, I want to cancel. Okay, we're just going to do this. Okay. Let's go back here. Bohr pretty much heated up gaseous elements, and he made them put out their light through exciting them with electricity, and then he saw the different spectra of the colors of each element. And so he really only worked on hydrogen, okay? That's it. He worked on hydrogen. We have seen these happen all kinds of other places. We've seen this happen with neon. Why do you think they're called neon lights? What's in them? Neon, the gas neon, right? So that's kind of cool. It's really, you think neon colors, oh, they're just bright and colorful, but neon lights come from the heated up gas of neon. And this actually is probably not neon. This one is probably hydrogen, because that looks just like the color of the hydrogen that he was just showing in the video. So different colors are coming from different gases. So you can have hydrogen and helium and iodine gas and neon gas and krypton gas. You can have all kinds of gases and heat them up. They will emit a certain color of light or multiple colors of light. Okay, so remember, I'm just trying to use the vocabulary here because this chapter 5 vocabulary is kind of rough. You need to know that a photon is a bundle or a quantum of light energy. There's other words like ground state, excited state we need to be very fluent with when we start getting there, okay? So that emission spectrum is a bundle of light that's being thrown out, okay? It's a quantum of light. So now you can use the word quantum, like, accurately. Okay, so there's not much else here I want you to really talk about. I've already talked about a lot of this. I'm not going to focus on here. We need to get to energy. So we're going to talk about energy, but now we need to calculate energy. So right now we only have under our belt how to calculate what? Wavelength and frequency, okay? Energy has not been a calculatable thing until now, okay? This is on your sheet? Believe so? Is it okay if the lights are off? I'm just going to sleep on me? Okay? You need to stand up at the lab station? Go stand up at the lab station? Okay? So we have the modern model of knowing how to calculate the energy of these electrons. And the first guy who helped with this, his name was Mr. Planck. Okay? Mr. Planck has his own constant. Okay, start by that constant. It is H. H is equal to Planck's constant, 6.626 times 10 to the negative 34. Write that down. That is a very, very important constant. What was the other constant we had? C, which was speed of light, 3.0 times 10 to the 8 meters per second. Okay, so notice these units, though. These units are joule times seconds. No division, it's joule seconds. JS, joule seconds. Okay, so I just wanted to point out his constant before I moved on. So what he did was he kind of followed Bohr, and he said, okay, we can heat up these solids, these gases, and we can relate somehow their frequency, their wavelength, to the energy that they're putting off. And so he created another equation, E is equal to HV. Okay, know this. E is equal to HV, and he allowed for us to then be able to calculate energy as well as frequency and wavelength that we already had been able to do. This is very related to Einstein's equation of E equals mc squared. I'm not going to go into detail about that right now, though. So we need to know this. What does this V mean again? Velocity, aka frequency, right? Because we don't know how to calculate velocity in chemistry, and maybe in physics, yeah. But we know this is frequency, okay? So tell me the relationship. If energy is equal to HV and you increase the frequency, what should happen to the energy? Increase or decrease? Right. Fast things have a lot of energy, right? Little dog, crazy, right? Lots of energy. So she moves fast. These are directly related. Because this H is a constant. You can't change it. So if you increase the frequency, you're definitely increasing the energy. If you're decreasing the frequency, you're definitely decreasing the energy. So which wavelength of light, red or violet, had the most energy? ultraviolet, right? Because they're short and they move really fast. Fast frequency. So we're starting to relate these things together now. Okay, and I'm not going to do the particle wave duality. I'll do this tomorrow. I'll do it next time. Let's calculate with this. So the two equations, they do hold each other's hands here. What is the part that relates to or is present in each equation? Frequency. So if you know frequency here, you can use it here to get energy. Okay, so you've got to be able to relate those two. So let's do some more practice, and then we'll kind of keep relating them. So a helium neon laser emits light of a wavelength of this. That is important. 633 nanometers. What is the frequency of light? So before we move on to this one, let's step back and figure out which equation is actually relevant. What variable is that as given here? So what variable is that? The lambda. Good. And then what variable is this? Frequency, so V, right? What equation relates those? C is equal to lambda times frequency, right? Okay, cool. So we know we have to use this one. The C is a known. We do know that. What is our question? Okay, so what's the frequency? So we know right before we even move on to calculating, let's rearrange our equation to solve for V. So tell me what I do again? Divide by lambda. Divide by lambda. Okay, so that cancels lambda out. So I'm just going to rewrite that over here. V is equal to C over lambda. What is C again? 10 to the 8th meters per second, okay? Over lambda. What's lambda? Wait, he says. Why are we waiting? Yes, we need to change that to what? Meters, okay? I'm going to do that up here. 633 nanometers. What was our conversion again? So what goes on top? 1 meter is how many nanos? 10 to the 9th. So that is 6.33 times 10 to the negative 7th nanometers. 6.33 times 10 to the negative 7th nanometers. So I'm going to get ready to write that for my wavelength. 6.33 times 10 to the negative 7th. Sorry, I don't know why I put nano. It's just meters. Meters. Okay, what can we cancel in terms of units right now? Meters and meters. What unit should be remaining? Per second. Good, like it. So calculate right now. 3.00 times 10 to the 10 to the 8th divided by parentheses 6.33 times 10 to the negative 7. So I'm really emphasizing those parentheses because if not, you're going to get some crazy numbers. Shout it out when you get it. I'm going to round up to 4.4 times 10 to the 14th per second, or hertz, or seconds to negative 1, right? Whatever we want to say there will work. Not whatever, like of those three. Okay, so again, we know how to get from nanometers to frequency, to meters to frequency. So using this same information, let's calculate the energy of that laser. Okay, so my next question, I'm adding it here, is question, what's the energy of the laser? All right, so knowing that information, what equation are we using? Equation HV. What is H again? Planck's constant. Okay, so of this equation, we know what two things do we know? We know H and we just calculated V, right? We have a purpose, right? We just solved for it right here. So this is V. All right, so energy is easy. Energy is equal to, what's Planck's constant again? Negative 34th units. Joule seconds, okay? So 6.626 times 10 to the negative 34th joule seconds. We're going to multiply that by the frequency. And I'm going to write it as this per second so you can see the cancellation of units a bit better. 4.74 times 10 to the 14th per seconds. So I'll write second out like that for you. Okay, So what unit cancels? Seconds, and that should like 100% make sense. What should energy be expressed in? Joules, and that's the only thing we got left, right? Yay, that's good. So this number times 10 to the negative 34th times this number times the 14th, so like 3 point something times 10 to the negative 31. Negative 30. Oh, I don't have this. You guys have to tell me. What'd you get? 3.9404. 3.14 times 10 to the negative 19. Oh, I was really off. Okay. Joules. There you go. All right, and that's energy. Okay. So, let's see what else we really need to do. If you're feeling okay with it, I'm going to try to stop doing some and let you guys practice some on your own. You guys do... Which one just looks more confusing? One or two here? What are you doing both? One? Okay. So, what is the wavelength of X-rays having a frequency of 4.80 times 10 to the 17th. What's hertz again? Per seconds, right? It's per second. So seconds to negative 1 or however you want to write it. Okay, so what equation are we using? C is equal to wavelength times frequency. Okay, so what are we really solving for? Or how do I rearrange the equation? Divide by V, divide by V. So wavelength is equal to C over V. Can you plug those values in? Do we need to change anything? No, you can just plug those straight in. So speed of light over this number. I'm not going to fulfill that. I'm just going to leave that there for a second just to give you a good setup. Tell me how to set up this next one. Or tell me what we know. Okay, look at this frequency. 98.5 megahertz. What we're going to have to do that one? Convert it to what? Just normal hertz, right? So I'm going to start off by doing that for you. Megahertz. What goes on the bottom? What unit goes on the bottom? Megahertz. And then the top, just normal hertz. What's the conversion? You need to write out King Henry died by drinking chocolate milk, ... We need to go that way, we need to go this way. Mega. Where do you think hertz lies on this number line? Base, so it's here. So the mega's over there. Mega is big, right? So 1 megahertz equals how many little hertz? 10 to the 6, right? 1, 2, 3, 4, 5, 6. 10 to the 6. So we're going to have a ton of hertz. So this is 9.85 times 10 to the 7th hertz. I think. All right, and remember hertz. If you don't like hertz, scratch it out and put it as per second. It's the same thing. So now we're in seconds, or per seconds. The question is, what is the wavelength of the radio station, or the wavelength of the stations broadcasted? So you guys know when you like tune into 106.5, the Pearl, or whatever it is now, 98.7. These are actually frequencies. So like when you turn your station to 98.5, it's megahertz. 98.5. Like that's what's on the radio. Like I don't know what station that is, but it's gonna be cool because it's a chemistry, right? Okay. So we would then calculate the wavelength by doing C is equal to lambda times frequency, isolating wavelength just as we did above. The hard part is kind of getting it started. After that, it's just algebra. Okay, let me give you guys take a 1 minute break. Get up and see somebody. Look back to me. Get up and give somebody a high five or something. I would have gotten an email about that. We have one later. So for homecoming. Alright, where'd you hear that? Who's your Who? Let me check my email.
Alright, come back to me. Give me 1 second. Come back to me. I'm gonna give you guys some independent or some partner work time because you guys need a break from me. Alright, so we have about 30 minutes left in class, a little more. Let's get through a couple of these practice problems, and you guys do not write on this worksheet. I know it's white in color. Normally white means like, yeah, it's yours, but I need it for next class too. You can work with a partner. You can move to a last station if you need to move. I want you to back up in your seats in about 20 minutes. So the first question, as you can see on the board, it's got a Model 1 white light and gives you a couple of pieces of information about those different colors lights. You already have the worksheet in front of you. You'll see that it says you can use colored pencils and color. Don't color, just move on. Just label it as red or yellow, blah, blah, blah. I want you to actually make it through a couple of these models. Kind of solidify some stuff you're talking about. So let's go 25 minutes. I'd like for you to get all the way through Model 3. All the way through Model 3. We'll see where we are here. I have so much stuff in that stack. So are you writing on your paper? No. I mean, yeah, you're writing on your paper. Are you writing on my paper? No, thank you. Okay, if you have questions for me, come up and ask me. I'm going to pass out some tests and etc. You might. You might.
Can tomorrow Archibald come to the front office towards the end of class?
Yes, thank you.
Thank you.